Okay, Wiz, we're talking about reasoning in latent space today. Is that the same as test time compute?
Yeah, that's right.
Nice, nice. Okay. And we've got two big ideas to cover that are aimed at scaling the power of LLMs during inference. Is that right?
That's right. So we have two, latent space methods. We have our continuous chain of thought, or coconut, right? And then we have our more directly, more budget forcing, recurrent depth model. Yes.
Ooh, man, woo, that's a lot. So when we look across both of those, there appears to be a pretty simple explanation. It's almost like, when we're in that sort of thinking space of computation, we don't have to do the thinky in words, and that's better. Maybe even it will allow us to find a new scaling axis. Is that right?
Yeah, that's exactly right. I mean, the idea is that we have this, we have this way of taking advantage of the most powerful thinking space in the transformer, and not just like for a second, right? Not automatically resolving back to token space, but kind of staying in this very in the mind palace of the transformer
Mm.
without having to write down the words. Yes, it's
Okay,
totally
okay,
true.
okay. So basically, scaling is dead. Long live scaling, something like that.
Yeah, scaling has died. We should scale.
Yeah. All right. All right. All right. Well, I'm pumped for the demos today. We're going to see some thinking in latent space. Let's cover all the concepts we need to get there. We'll get you back in for some discussions along the way because this one's pretty meta. Thanks, Wiz. All right, guys, we are going to rock out on large reasoning models today. And while we were originally going to just cover chain of continuous thought, or coconut, we saw a paper come out a couple weeks ago on recurrent depth right along these same lines. So what we're talking about today is reasoning in continuous latent space. That's the common thread. We're going to really try to grok what that means, try to visualize it, and then go build, ship, and share some awesome stuff with both Coconut and the new recurrent depth approaches. Also, we'll talk about implications of scaling and where all this is headed. It connects back to test time compute and all the stuff we've been talking about in our LRM series. If you have questions along the way, please do put them in the Slido link, and we will get to the most upvoted questions at the end of the sesh. If you want to jump in on YouTube or on LinkedIn Live and throw a comment in live, please do during the discussions, and join us in investigating this really cool new space. All right, with that, let's go ahead and hop right into it, guys. Today we're talking about reasoning in continuous latent space. All right, so we want to kind of wrap our head around all of these key words, and this is a really, really cool idea when we can finally start to grok it. So I hope you guys are feeling as excited about it as I am by the end of the sesh. Ideally, after this hour you spend with us, you're going to understand reasoning in continuous latent space, including the continuous chain of thought, or coconut, and recurrent depth approaches. We want to discuss the impact of this kind of approach on test time compute scaling, some of the working hypotheses, and some of the things people are interested in looking out there on the LLM edge for as we continue to see the field progress. I want to demonstrate both approaches and check out the new Coconut library as well. So how we're going to go through this is we're going to essentially introduce this idea of reasoning in latent space. Then we're going to talk about the scaling part of this before we dig into the specific approaches, and we get the demo on both approaches by the end. So it should be a lot of fun today. Let's go ahead and dig in. Reasoning in latent space. Let's root ourselves first in some definitions. When we talk about reasoning, we're talking about the action of thinking about something. And it's kind of funny, in a logical way. If you look up logic, it uses the word reason, and there we are, caught in a loop. But reasoning is about thinking. Latent space is about using a representation of our data that sort of captures the essential features of it. We can think of latent space as embedding space, or the space of math and numbers. In other words, it's just not the space of words and natural language. Let's think about how this manifests in a transformer architecture. Here I'm showing a GPT style architecture from the GPT-2 paper. What we want to think about is we want to put a sequence in, and we want to get some next token prediction out. When we put the sequence in, we're in the space of natural language. When we get the next token out, we're in the space of natural language. Betwixt and between, we're going to be in latent space. We're going to be in embedding space. We're going to be in the space where we can do math and stuff. And importantly, we can kind of think that we're putting in this big old sequence, you know, especially if you think of these long context LLMs, we're just jamming context in there. And then we're popping out bloop, one token, one single token, okay? So really, at the end of the day, you can kind of think of this as we're kind of doing this compression, okay? We're taking all of this possibility space and all this crazy, and then we're just like, bloop, one token. We just want one. So it's kind of interesting to think off the bat that LLMs, in this sense, are kind of giant compression algorithms. We are condensing all of that information into one of, let's just call it 500,000 different tokens that we might have. There are many different sizes of possible vocabularies, but let's pick a big number that is on the order of magnitude of something we might see, hundreds of thousands here, down to one. Now, let's think about this a little bit more. The model itself doesn't really need tokens, okay? We need the tokens. The model is cool with just the compute space because it's happening in a computer, right? And so for this reason, you'll start to hear people talk about tokenless reasoning. And this is the idea of reasoning in latent space. We're sort of doing it without tokens. And the hypothesis here, the scaling hypothesis, you might say, is that going tokenless can allow us to scale. Okay, hold on. Let's discuss this hypothesis. Wiz, come up for this one. So going tokenless can allow us to scale. That seems a little weird to me. It's not very intuitive. What's your intuition behind this?
Yeah, so the word tokenless is a fun one. I would say, like, the idea is we don't need to resolve back to tokens to scale because we can just keep looping around before we get to tokens, right? Really, anything that allows us to keep looping around until we get to the final answer is going to allow us to scale, right? Because we can say, well, loop more, right? Like with say like generating a response, right? If I generate for 5 tokens versus if I generate for 70,000 tokens, right? Like we have this idea of a scaling axis on the inference side. This is just kind of shoving that inside the model architecture as opposed to allowing it to resolve the token space. Okay. But the idea is we're still adding information at every step, at every stage, right? That we do a loop, as it were. So we're getting a better and better and better and better and better response.
Okay. So I'm kind of imagining, okay, I have input, I have output, I have a black box in the middle, and this sort of like scaling of the black box in the middle, just in this sort of, you know, latent space of the black box in the middle. Is the latent space itself being scaled, or what is being scaled precisely if I look inside deeply that black box in that latent space? Is it that I'm just using a lot more of the latent space? Is that I bigger embedding models? The intuition's a little bit tough for me How does it come across for you? And we will go into more detail, throughout the presentation today.
Yeah, I mean, like the big idea here, right? The big fun thing is that we have thousands and thousands and thousands and millions, right, of points on the line that we can exist in latent space, whereas we're like kind of owned by 500,000 tokens in token space. Like having every floating point number in every single element of the dimension embedding, right, can be expressed in latent space. So even if we only had, 20,000 numbers we could represent per element, but we have 4,000 elements, you do the math, big number, right? So
more than 500,000.
More than 500,000, certainly, right?
Okay.
And we also
We've scaled it up at that point.
We've scaled it up. We have more nuance, right? We have like very slightly different as opposed to massively different, right? And this allows us to be more expressive. Yes, we have to get back to token space, right? But while we're thinking, while we're in the mind palace, it's like in your imagination, right? You can imagine the largest of buildings. You can imagine yourself walking through a castle, things like this, right? Even though in your physical space you've got a pen and paper, right? It's like this is the idea.
Okay. So on the computer level, we've got this 32-bit representation of sort of each floating point number in our embedding representation.
That's right.
And so that can just like, whoo, okay, we're way above that number of tokens that we might have off the bat. Okay, and then there's this sort of human level sort of intuition that I have, which is like, it's like, wait, hold on, let me think. And when I'm frozen, I'm not thinking in words. I'm thinking somewhere in my latent space of my mind. Like I'm not thinking complete word thoughts. I'm not going through that arduous next token prediction in my head. I'm kind of exploring all the possibility spaces. And this is, I think, my intuition behind this latent space idea and going tokenless is we often do this. You see people going tokenless in their latent space reasoning compute in their mind when you talk to them, right?
I mean, and that's in fact, we have to resolve thoughts to token space all the time, and it's incredibly frustrating, right? Like when you're trying to describe an idea that you just don't have the words for, but you intuitively in your mind you understand it well, and you're struggling to get it out to the token space. It's the same thing in the model. Obviously, we're anthropomorphizing a lot, but the idea is there is a parallel to that process that exists in the model.
That's right. And how many times have students said, I know it, I just can't tell you it.
Yeah.
There it is. There it is. Okay. All right. Beautiful. Wiz, thanks for your insights. Let's keep it moving. So as we think about scaling, what we want to do is we want to think about this idea of test time compute along with scaling in the story and in the way that we've gotten here. Scaling, of course, started way back in the day with the multi-layer perceptron artificial neural networks and single neurons to many neurons and so on. But it really, really got going with deep learning. And we saw, we train bigger and bigger models, we get better and better output and results. This has been known for years. And it's known even today. I mean, this is from the CEO of Anthropic, Dario Amodei. And, we want to think about the place that we are based on where we've been. I want to put this in context here. So we go from pre-training, which is the thing that sort of takes a long time. It's the Shoggoth. It's got all the possibilities. We can sort of think of this as months, many, many tens of thousands of GPUs, maybe more these days. And as we saw at NeurIPS this past year, Ilya Sutskever noted that pre-training as we know it will end. Now we've seen that there's been a lot of focus subsequently, especially out in public, on post-training and on this idea of RLHF and RL. And we've talked about this in our recent reasoning model events. And when we think about this post-training phase, it continues to grow in scope and scale. And it's been a real focus area beyond pre-training. We sort of, you see a lot of companies coming up like RC and others that are really, really focused on this post-training piece rather than on pre-training from scratch. There are very few people. It's almost been commoditized, the pre-training from scratch. So this phase of post-training is getting larger and larger. And we see this coming to fruition in things like O1, where we'll do some of this post-training RL, RLHF, where we start dealing with these very long chains of thought. And this is where this idea of test time compute came up. And this was a paper from Google in August last year called Scaling Test Time Compute. You know, it's basically taking that scaling paper originally and saying, well, now we have this sort of other axis to scale on. And again, this is the idea that we're anthropomorphizing a little bit, but humans tend to think longer on difficult problems. Maybe we should let machines do that. And when we think of test time compute, it's just time spent thinking, you know. And so if we think about kind of how we can leverage this, we've seen some of these things come out in recent weeks and recent months. We talked about DeepSeek R1 just last week. And, you know, this is the same idea. It thinks before it answers. And this is, again, just a sort of the next step in the evolution of what we've got going on here. And we saw, moreover, DeepSeek R1 generates one token at a time. It's able to spend more time processing, and it generates these thinking tokens that explain its chain of thought. So we're generating tokens during our chains of thought, and that makes them explainable. Very cool. All right, I want to bring Wiz back up for just a moment here. Okay, just to be super clear, reasoning and test time compute, do you think these are sort of, you know, triple equals sign, or how would you say, you know, generally we're talking about the same thing, but they're not the same thing?
Yeah, they're this. So okay, they're not literally the same thing, of course, but they're also pretty much the same thing in how we talk about it in 2025
today. That's right.
So reasoning is right now, because our models are system one machines, right? They're not reasoners. They just do, right? We need some way to stretch them into this reasoning domain. And the way that we do that is through some kind of test time computer, some kind of test time scaling. Things that, you know, it's interesting to think about, but something like an agent, right, is an example or expression of test time compute, right? We're using the agent to leverage more compute to do cooler things, right? So these kinds of systems are also test time compute. Very broad definition. You love broad
agents are also reasoning, right?
So that's right. Agents are reason. There you go.
Oof.
But the idea is that we need some way to stretch the system one machine to a system two machine. And the way that we know how to do that right now is through these test time compute methods, where we spend more time on inference as opposed to changing the architecture, doing more pre-training, or et cetera, et cetera.
Okay.
Yeah.
I like your caveats of that's what we're doing now. Let's zoom out a little bit here, and let's you know, these breakthroughs that we're seeing, you know, and they're just coming, pre-training, post-training, and now test time compute. Like, when you look out and you look at the field and how it's emerging, I mean, one of the things that is important to note as we dig into Coconut next is it feels like it's the right time to dig into this latent space thing. Why is that? Why is this an obvious next step?
Yeah, we talked about this, you know, when we prep for these events. Obviously, it's not a surprise, but we talked about this kind of thing when we were prepping for this event. And I think the discussion was good because we've been through this history so many times, right? Like with deep learning. Deep learning was a good idea the day we discovered MLPs, which was ages ago, right? But we lacked the circumstance for that additional depth, you know, to be practically useful. And it's the same thing now, where we're coming up against a wall. If you remember Ilya's words, right? Pre-training is dead. Not really, but we're running out of data. Pre-training is hitting, it's slowing down, it's plateauing, right? And the idea is that we have some thoughts that say, well, we need to keep progress going. So what's the next lowest hanging fruit that is accommodated by our hardware? And that's why it's like, oh, well, we can just spend more time doing inference then, right? We can do inference so fast now that spending extra time in inference is feasible. What would have used to take months or at least weeks now can take a day or hours. And so it makes sense. The circumstances have changed. We're running up against a wall with our tried and true bread and butter methods. And so now is the time for these, for these kinds of leaps of progress.
Yeah. And I remember, when we were teaching like the AI Engineering Bootcamp in early 2024, a lot of people were having, issues with streaming the tokens out, and a lot of people were, it's like it's just becomes so much easier to get. You want a quick result? Boom. GPT-4o mini or whatever it is, whatever equivalent of model, are so good at those quick results, those sort of system one results, that now we're like, okay, well, what if we want to tackle bigger, beyond a single task kind of problems, like we're seeing with deep research, like we're seeing with these other things that require it to go chew on some things. But I want to also just dig in there real quick, because you mentioned agents, and when we think about deep research or some of these types of tools, they're actually agentic and they're using tools. What we're talking about here is we're talking about reasoning inside the LLM, and we're talking about doing engineering within the LLM, and sort of giving the sort of the brain itself instead of the application. We're not giving the application cycles. We're like giving the brain itself cycles to think here, right? Is that approximately, where you see where we're at, and then where do you see this headed, at least for the rest of 2025?
Yeah, that's exactly right. I mean, we have time, to spend because our inference is so fast.
So good.
And we're back to where we were before, right? So LLMs are a black box. We know that. But these chain of thought things were really nice because we can see the thinking. But now, in order to get to the next stage of scaling, right, we kind of got to go a little bit more into the black box. We got to go
into
back
beyond,
into
the unknown. Yeah,
it happens, but it's the timing is right, and with companies like NVIDIA, with companies, the other accelerators that are coming out, they're super good at inference, Grok and Samino, all these other peeps, right? We're getting real fast at inference. And so the spending that time, it becomes less and less impactful to the user experience. But more importantly, we have a lot of applications LMs aren't good for yet, where we don't care about response latency, like research, like PhD level math, where it's like, it doesn't matter if it takes a day. Yeah, because that means it didn't take some other person a day, right? Like that's the we're at this time. The models are capable enough that we can think about problems that we can't just do ourselves faster. The whole ecosystem is set up for this to be the right time to push reasoning.
Oh man. Okay. All right. There's so many rabbit holes. Let's avoid them and let's keep it moving. Thanks, Wiz, for your insights on that as well. Let's get into Coconut, guys. Let's talk about how this actually manifests itself. Again, big idea. We can start at the very high level. We can say this is about latent space. It's not about language space. Okay. This is about, and this is exactly what you'll read in the paper. You'll read language space may not always be optimal for reasoning. Let's go. Okay. Yeah, we got it. And we want to utilize the last hidden state of the LLM as a representation of the reasoning state. When we say hidden state or latent space or embedding space or this sort of space of math and computation, we're talking about the same space. Of course, the exact state of the space changes depending on where we are in the transformer. But let's take a look at the image from the paper. In a typical chain of thought reasoning model, we're going to ask a question, we're going to generate some tokens, and we're going to think kind of out loud. We're going to let the chains of thought flow. When you click into the chain of thought on O1, as we've seen before, you can see sort of in the side panel the steps it's thinking through. Now, conversely to actually thinking out loud, we have here that the last hidden states are used as input embeddings. Okay, well, what does this mean? Well, let's go back to our GPT-2 style diagram and think about this. The input embeddings here are where we're essentially looping back to. So what we do is we kind of loop back before we generate the next token, right back to this embedded space. And I'm basically gonna run through again before I give you the next token. I'm going to keep chewing on it. I'm going to keep thinking about it. And this could be, you know, in GPT-2, this was 12 different decoder block stacks. You can imagine a lot of different configurations and ways to do this. But essentially, what are we doing? We're avoiding that compression by staying in the latent space. Okay, we're avoiding that compression because, of course, when we do the actual prediction of the next token, you know, this is my little transformer here. This is from the illustrated transformer that also has an encoder and a decoder stack. But the point here is to look at the next token prediction to realize this is the GPT style decoder stack. And we are having an actual compression there when we do that prediction to the word. So we want to avoid that by using the hidden state representations. And I also want you to note here, we use these beginning of thinking, end of thinking tokens. Remember, we saw this mentioned earlier in the talk today by Jay Alomar, because it's able to spend more time processing through the process of generating thinking tokens and explaining its chain of thought. Now, if we look a little bit closer at the paper here, we can see that we can actually, you know, put a language modeling head on each hidden state and decode and pop out the token, but we don't, okay? Because obviously that's kind of the point, that we're not doing that. And so it is more of a black box. If we wanted it to be more explainable, we would need to do more intermediate decoding. So it's harder to know exactly what it's thinking. And if you've been following our content a while, this language modeling head, you might notice from this, you know, widely now shared LLM visualization, this is just the very last step. It's the very last piece before we actually do our next token prediction, after we've done all of our embedding and matrix multiplications with attention, feed forward layer, residuals, add norm layers, etc. Okay, so takeaway from this, big idea, we don't need to use tokens directly. Coconut came in and they're like, yep, can do. And that's pretty dope. And it's pretty dope, not just because a bunch of researchers got together and said can do. It's pretty dope because it might actually be super useful in 2025 for real products, for real people, for industry. That gives us an entry point into the recurrent depth approach. So let's go deeper. Let's recur what we just actually did with Coconut. Now let's talk about scaling test time compute with latent reasoning, a recurrent depth approach. This is from just a couple weeks ago, February. So now, same idea, not using language space, using latent space, and we're doing it via recurrent depth. Now, the diagram from this paper that you need to check out, that you need to know about, is this one. test time compute recurrence. But I'll tell you right now, this one might not help you truly understand what recurrent depth really is doing at a calculation level. At test time, the model can iterate longer to use more compute and improve its performance. Okay. Instead of scaling test time reasoning by verbalizing in long chains of thought, the model improves entirely by reasoning in latent space. So this was to, I believe, Richard Gower's question earlier. Tasks that require less reasoning, like open book QA, converge quicker. This is very cool than tasks which need more reasoning. This is the key insight from the paper. The constraint that expensive internal reasoning must always be projected down to a single verbalized token appears wasteful. It's plausible that models could be more competent if they were able to natively think in their own language of continuous latent space. They are computers, after all. Our proposed transformer architecture is built upon a latent depth recurrent block that is run for a randomly sampled number of iterations during training. I can't see it. Let's see what they gave us in the paper. They gave us this bad boy. Personally, not a fan of this diagram. Wiz thinks it's totally fine and it makes perfect sense. Let's see if we can break it down for you guys here. A visualization of the architecture. We have the prelude block, we have the recurrent block, recurrent block, recurrent block, and then this coda. So each block consists of a number of sublayers. Okay. The blue prelude block embeds the input into latent space. All right. Where the green shared recurrent block is a block of layers that is repeated to compute the final latent state, which is decoded by the layers of the red coda block. Back to our GP2 architecture diagram. Let's think about how we're still kind of doing this loop back. We're still doing this reasoning in latent space. And now let's label the prelude, the recurrent block, and the coda. We want to think about the recurrent block as an entire block or stack. This is the useful way to sort of take this to the next level. And what we want to do is we want to imagine that now we're going to set this up so that we're going to put a bunch of recurrent blocks kind of in parallel, recur to occur again, right? And we're going to set it up so it looks something like this. We have a single prelude. We have one recurrent block. We have two recurrent block. We have n recurrent block. And then we get a single coda or output. You can configure this, as Wiz will show you in the code, many different ways. And this is the big idea. And it's a natural extension, sort of depth-wise, to what we saw with Coconut. So the big idea here is that you don't need to use tokens directly. Same big idea as Coconut. Recurrent depth says, just like Coconut, yeah, we can do it. And maybe, it could even be more efficient, especially with tasks that require less reasoning, like open book QA. Converge quicker, observations. We can hypothesize that maybe, just maybe, we could scale this out and we could be like, I don't know, better, faster, and cheaper. Wiz, I want to bring you up to talk a little bit about takeaways before we get into the demo here. So is the recurrent depth approach just better then now? Like, is it just the next step? I mean, what's your take on this?
Yeah, I mean, so no, not better. It's definitely different. It's definitely it's trying to do a different thing, which is dope.
Mhm.
I would say, like, at the end of the day, they're using the same process, but they're finding different ways to take advantage of that process. The recurrent depth is more of an architecture change, right? It's more of a, let's actually get this reasoning inherent to the model. We're going to train it to be very good at this recurrent task. We're going to train it to do this accordion thing that it does very well, right?
Sure.
Versus Coconut, which is like, let's adapt and add to existing architecture, right? To get this kind of reasoning flavor that Coconut winds up getting. So it's the same process, two different approaches though, right? They're coming at it from two different angles. I would say, like, recurrent depth is interesting because it's got budget forcing, right? It's obviously designed to scale as you need it to. However, Coconut, is, I mean, it's great. It's just chain of thought, but inside the model, right?
That's
So
right. That's right.
both good, both definitely good. I think we're just seeing these latent space approaches kind of flourish right now, and I expect that we will continue to see them flourish as we go on together.
Yeah, and this is kind of interesting, right? Like, this was released, but not by Meta AI, but by Facebook Research, right? And so the recurrent depth approach was also done by researchers at Lawrence Livermore and elsewhere. This is not something that product teams are using today. This is very much a research grade thing that is cool, and we're seeing some early signs that it's potentially quite useful. I want to zoom in on like, just when people think about the actual how of this, when they think about actually implementing this in maybe one of their applications. So whereas in the Coconut space, you're going to go and you're going to like, oh, nope, not going out into natural language space, just going to sit here and chew on it, and then I'm going to pop out my final answer. So all you get is final answer, baby. It's called a black box. Okay. When we go to the recurrent depth piece, you said something interesting earlier when we were chatting about this, and it was like, I'm going to think and think and think and think and think, and all of a sudden I know, and I'm going to do that just with one token, is sort of the recurrent depth paper, and then I'm going to let the rest of the tokens stream like normal, right? So there's this real interesting idea of like, which things are you thinking about? And this is where the idea of a beginning of thinking, end of thinking token, or a beginning of sequence, end of sequence token comes into play. You can think about the sequence, or you can think about the thinking. Does this make sense?
Yes.
Okay.
Yeah. We can think about the thinking, right? So we can double it up. Yeah, we can think about the thinking.
Yeah. Okay. So recurrent depth, in short, I mean, is like, you think about a single token and then you let the sequence go. Like, that's what I thought was interesting, and maybe that's not exactly right, but that was my understanding.
Yeah, I mean, so that's not yet what's happening, but the idea is that this is complementary. So the idea is that we have these, and they call it out in the paper, which is why we're bringing it up, right? But the idea is that we have this complementary suite of scaling tools that shouldn't interfere with each other, right? That should allow us to go forward unimpeded, and that's the idea, right? So we can marry these methods together. They're not yet married together, right? So we still decode one output, right? We're not decoding like a token at a time, but you can certainly put this in a loop where it's going to think a lot about the next stage of thinking, right? So we can imagine like thinking through a process step by step. We can blow those steps out, and for each of those steps, we can use recurrent depth, blah, blah, blah. There you go. That's the idea.
Yeah. So like,
this is a circumstance thing, right?
Right.
We don't have the circumstance yet for this to be a brilliant solution, right? We don't have so much compute that we could just do this willy-nilly yet. but it's there. It exists. It's possible.
Yeah, I mean, it reminds me of why we don't design like, like hammers at the level of the atom, right? It's like
Yeah.
we've got sort of this idea. Maybe we could call it system one is GPT 4.0 mini, and then we could say, okay, reasoning model that's spitting out tokens is like system two, and then maybe like we've got this sort of system three that's in latent space, and then we've got this like system four that's like on any given specific type of thing I might want to extra think about in latent space, I might go deeper on it. So there's just this real sort of very interesting abstracted meta thinking at play here. And it gets back to me to sort of the idea of like kind of meta learning. I mean, they really did away with our ability to use that term in the GPT-3 paper. So we're at the end of sort of the words that we can concretely say we know what to do, but we know what to do with the code. So I want to go ahead and just quickly introduce this to you. Wiz, we're going to do a quick demo here, and we're going to use the official implementation from Meta on Coconut, as well as look at recurrent depth. Wiz, I'm going to go ahead and hand it off to you to take latent space reasoning for a spin for everybody.
Yes. Okay. So let's take it for a spin. We've got a repo to look at, and then we've got a model to look at. So Coconut includes all of the training code and everything, but does not include the actual model. So we're going to look at the recurrent depth model since they published the weights. Way to go, them. So we already have seen these kinds of diagrams. That's great. Getting started is easy. If you want to train your own Coconut, which I don't necessarily suggest that you do for sure. But basically what we have is we have our coconut.py. Our coconut.py has this idea of, basically just hacking the normal, the normal kind of the usual, I would say, transformer architecture. So we have this idea that we can, do the kind of latent tokens, right, which are not actually manifested tokens, but we still need to keep track of them. They're still part of a sequence, et cetera, et cetera. Then, of course, we have our actual processing of this, where we're going to do this little pass in the max number of latent steps, right? You can see all we're doing really is just looping around in this pass, right? So we're not doing much else than that. Right. So you can see like there's no real like big modification here. We just take the end of the thing. Instead of doing more tokens, right, we do latent space thinking. We just loop through that latent space. And then eventually we want to go ahead and we want to send this to token world, right, where we're going to use our base causal LM. So this is our normal LLM. And the idea is because when we create the next token, right, when we're actually generating our next token, we don't have and this is most apparent in our generate step, right? We don't have the idea, like the tokens are in their embedded form, right, inside the model. So we don't have to decode them if we already have them decoded. And this is kind of like the brilliant idea of Coconut, right? Again, we just have this little loop-de-loo, and all we're doing is we're saying, hey, don't exit into token space yet. And then when we finally do need to exit, we can just put a special token and then say, okay, now we're going to go back to token world, right? We're going to start decoding into the token output. And that's really it. Like you'll notice this is a 270 or whatever line file. That's the big change, right? And the only thing that's really different is that we have this little mini loop where we're going to say, hey, we're going to think around in that embedding space as opposed to going to token world. So how did they get the ability to do this, right? That's like the big question. So how they got the ability to do this is most clearly expressed through this diagram, which is basically saying, how did we do this? How did we get here? Well, we took a query which had chain of thought steps and then eventually an answer. And essentially what we did is we trained the model by slowly eliminating the steps, right? So we slowly eliminated the actual steps. So you'll notice at first we're going to train the model in order to give it these special beginning of thinking, end of thinking tokens. Then we're going to replace step 1 and we're going to shove it in the hidden space, right? In between our beginning and end of thinking tokens. Then we're going to train it on 2 steps missing. And then we're going to train it on all steps missing, right? This is the idea, is we're slowly tucking that reasoning process into the latent space. But the key here is that each of these thoughts is still another pass, right? We're still able to think in steps in latent space. We're just not resolving to token world until the end. But this is the big idea of Coconut, right? This is slightly different than the big idea from the recurrent depth model, as Greg has already outlined, where we're actually going to dynamically create blocks of recurrent depth or recurrent thinking at time of inference. This is much more immediately scalable by humans, right? Because there's a parameter now, which is how many blocks do we want, right? And the big thing about this model is that it works with the minimum number of blocks, which is going to be 4 in this case. So the default, recurrent depth model is going to have, 8, for instance, 8. I'll go ahead and share the Colab link definitely in the chat. But it's going to have 8 total layers, right? Because there's going to be a number of layers per recurrent block. As well as a number of layers in our prelude and coda blocks, but we can just decide to make it arbitrarily large. Now in the paper, they say it should be at least 4 recurrent blocks, right? Plus the prelude and coda. And it should more likely be closer to 16, right? But you can go to 64 and potentially see some increase. So let's see how this thing actually goes. Let's see how it works. It's just a Hugging Face model, so we'll zoom in a little bit more. We load it the same way we always do. Auto model for causal LM, auto tokenizer, nice and easy. We're loading this thing in bfloat 16 just to keep it small. We download it. It's great. We're going to choose our device appropriately. You're going to be hard pressed to run this outside of a Colab notebook with a GPU instance. So make sure you have a GPU. And then we can set it to eval mode. We're going to set this config as provided by the actual model card for the recurrent depth model. But you'll see that we're fairly short max length, right? We have these stop strings. This is strings where we stop the generation, right? We have use cache. So this uses KV cache, right, in order to do good at its job. But what this means is that we have to say use cache. There's a lot of instructions on how we can exploit the KV cache in the model card, which is very fun. And then, of course, we're going to have a bunch of other generic hyperparameters for generation. And then we can see our actual model, right? So we have our transformer model, classic. We have our text embeddings, classic, right? And then we have our prelude block. Then we have some adapter that adapts between the prelude and the rest of our blocks. We have our core block, which is going to be, it's called, I'm not joking, the sandwich block, right? And that's going to basically be these are the 4 layers that exist inside our recurrent block. So there's always going to be one of these recurrent blocks by default, right? With 4 layers. That gets us to 8 layers total. But the idea is here that we have this adapter between our prelude and our recurrent blocks. Then we have our n recurrent blocks. In this case, it's just 1 with its 4 layers. Very cool. And then we have our coda. Our coda is just, again, the thing that gets us to text world, right? To token world, because we have to decode what these recurrent blocks have been thinking about, what they've been stirring on. So we're going to look at an example of how to actually use the thing. It does support templates, so chat templates, just like most models. It wasn't explicitly trained for this task, so you're going to see some quirkiness and funness and weirdness, but it is still possible to use it. And we're just going to ask some GSM 8K questions. Natalia sold clips to 48 of her friends in April, and then sold half as many clips in May. How many clips did Natalia sell altogether in April and May? Classic math question. And you can see that we send this through, and that this step, right, this nums step, or this num steps parameter is the thing that says how many recurrent blocks do we want, right? So in this case, we're going to say 4 because it recommends using at least 4. And that's the reason why. And you can see that we get this response that she sold 96 clips because she sold 48 plus 48. Hey, well, that's not correct, right? That's wrong, in fact. So maybe if we juice up the number of steps, it'll be less wrong. So let's go to 8 recurrent blocks instead of 4 recurrent blocks. And again, the only thing we're changing is the number of blocks that's going on, right? And we get here, and then we get the correct answer of 72. Hey, nice, perfect. And then we do it again, and we get, again, the correct answer. So at 16, it's also correct. That would be assumed. Let's try another example. So we have this next. Ken created a care package to send to his brother who was away at boarding school. Ken plays box, blah, 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 blah. Is another math question, right? Okay, let's see it. So we get here, again, we're going to start at 4 steps, and then we're going to see if it did it. And we get the weight of the box of double the weight of the box of gummy worms. So it just becomes nonsense, right? Like this is not a good output. 4 steps was not enough. The model produced garbage. Let's try 8 steps. All right, 8 steps now is less garbage. The final weight of the box of goodies is 12 pounds, but it's wrong. That's not correct. So 8 steps won't do it. What about 16 steps? And again, we're not reloading the model. We can do this every time we do inference. Every time we call inference, we can change this number, and it's going to use a certain number of blocks, right? So think about if you have a classifier that classifies how difficult the question is, right? You can say for very difficult questions, use more recurrent blocks. For very easy questions, use less. Maybe don't use 4 because it produces garbage. But then we see in the 16, not only do we get the correct answer of 16 pounds, but we also see the classic let's think through it step by step pattern emerge, right? So this is the idea. We add more blocks, we get more think, we get more accurate. Such is the world of reasoning. There you go. I'm going to pass you guys back to Greg, who can take us into some Q&A. Before I do, please remember to like and subscribe and ring the bell notification. We're live every Wednesday doing this. We love doing it. There you go. All right, back to Greg.
All right. Yeah, let's go. Got the thinky going, and it actually worked. What a beautiful thing. All right, let's go ahead and wrap up and take some conclusions away from the day before we get into QA here. You know, the big idea that hopefully you're walking away with today is that we don't need to use tokens directly for reasoning like we do, but LLMs don't. If we don't use tokens, we get this less compression effect. And Coconut showed us this can be done. Very dope. And recurrent depth tells us maybe it could even be more efficient, especially if we start thinking about tasks that are really optimized for this kind of approach. Going tokenless might allow us to scale tokenless. We'll get into the pedantic, persnickety details of that in LRM events to come, I'm sure. That is, we could potentially use fewer tokens to get the same response in less time. Maybe we could even get better responses and get the trifecta. Okay, I want to go ahead and go to QA now. If you haven't put your questions into the Slido, go ahead and throw them in there now. Wiz, let's take a look at the QA. We got some great stuff going today. I want to kick it off with Jan Boers. Is it possible that after the process of reasoning in latent space and then trying to verbalize the final answer into human language, it's unrecognizable? I mean, I think we kind of saw some of that just a minute ago in the demo.
Yeah, you can definitely do that. It's hard. So your strategy is going to depend on, or the efficacy of that solution is going to depend on your strategy, but you can certainly try to get some of that information back out of the latent space. Remember that the latent space thinking, right, still counts where we're generating tokens. So it's going to be, it's going to depend on the strategy that we're using, how we're decoding, are we decoding all of it, et cetera, et cetera. But we can definitely get back to token world, though the process might be more computationally inefficient, and so might not be desirable, aside from areas where we need explainable explainability. Yeah.
Yeah. I also really just think this is kind of a sidebar. I kind of really like this intuition of like, if we're learning all the languages of the world, then this very rich token space beyond what we can sort of imagine in our minds starts to make a lot more intuitive sense. Okay, so going to the next, we got a bit of a meme question here, the little memer dreamer action for those of you out there from Anonymous. Do these techniques change the fact that LLMs are just stochastic parrots?
It does nothing. It does nothing to address that.
All right,
Yep,
moving
there
on.
you go.
Anonymous, have there been experiments done yet with no positional encoding in the prelude block?
I don't imagine so.
Yeah.
We still care about sequence order, so we still care about position in language. So mayhaps there's some way where we don't care about the positional information when we're thinking around in latent space, but that experiment has not yet been run. And my intuition would say that we want to keep some positional information just because language we do have to resolve back to language at some point, and that should hopefully make it easier. Yeah.
Maybe if indeed time is a flat circle, it would work, but I'm not sure. Okay, so let's go to the next one here, Anonymous. Any research on different embeddings and their impact on the recurrent depth approach? I would imagine this is something they've talked about in the research groups that are working on this. But I mean, this was sort of one of my questions too, is like, does it matter? And of course it matters. I mean, what's your take on this, Wiz?
Yeah, it must matter. I don't think we're that deep into it yet, but we are like, they are using a transformer model to generate the embeddings. I'd imagine that we'd see a lot of fun work based on this, exploring different embedding approaches beyond just this work. It should have some impact. What impact is remains to be seen.
Nice. Okay. Does the collab run on T4 GPU? Free 99?
You'll definitely be able to run up to 8. 16 might be a little hairy.
Okay. All right. Yeah. And then final question from the Slido today from Anonymous. The embeddings link between internals of the transformers and tokens through the dense network. The embeddings link between internals of the transformer and tokens through the dense network. I would think thinking in latent space relies on hidden states. I think there's a disambiguation of language thing here. I want to clarify my understanding, and maybe you can sort of triple down on it, Wiz. Like when we talk about hidden states, when we talk about embedding space, when we talk about latent space, when we talk about math and compute space, we're talking about the same thing. It's just not language space. I'm not sure if that addresses the question or if you have anything to add here, Wiz.
No, nothing to add. I mean, if I understand the question correctly, we don't care about going to token world until we do. We do stay in embedding space until we exit. In either case, so I might be misunderstanding the question, but we don't need to go back until we do go back.
Okay, and then I think related to what you just said, we've got Oliver Mills in the YouTube chat here. Can you pull out some of the reasoning for transparency? Realize the cost but value. I'm not sure what the last part says, but the first part, I think the answer is yes.
Yeah, it must be true that we can squeeze some juice from this. I don't know how productive that would be exactly, but we must be able to. Remember, though, that each step that's occurring in the latent space, right, we would basically just decode back into tokens. So that it might not make sense because it didn't have to make sense in token world, right? So we can get maybe a summary or something like that, but to go directly to, we'd have to build in an additional process, and that additional process would kind of be a spoiler, holding us back computation.
Yeah. Right. We don't want to put that extra burden on it. Otherwise, why do we go do this in the first place? Okay, Wiz, thank you for all of your amazing insights today. We look forward to the next LRM event in the series. And it's time to go ahead and wrap up. Shout out to some of our great community members in the chat today, including Sahar, AI by AI, Black Courant. Great to see you guys out there. And shout out to Salil and Wayne as well. I'd love to see the regulars coming in. If you haven't joined our community and you aren't a regular yet, it's a great time to jump in and join us. In the Discord, I am live every Monday with a growing group of people telling you what they're building, shipping, and sharing this week, including some of the folks I just mentioned. And we are there to hold each other accountable, to really get after it and achieve our dreams at the LLM Edge. If that's of interest to you, come join us next week for free. If you want to accelerate your LLM application development, consider joining the upcoming cohort of the AI Engineering Bootcamp. This will be cohort 6, and we're excited to incorporate more reasoning. We're excited to incorporate more vision language models and multimodality. We're excited to incorporate everything that is really kind of production ready at the LLM Edge, including what we're talking about next week, which is Cursor, probably one of the most hype AI tools out there. If you haven't dug into Cursor yet, you got to get into it. We're going to be doing some vibe coding with Wiz. This is like coding in natural language. It's going to be a ton of fun, and it's going to be a real blast of an event. So join us next week live on YouTube, same time, same place. You know where to find us to talk Cursor. It's a guide for AI engineers or aspiring AI engineers or people trying to lead AI engineering teams. And with that, we'd love to hear any feedback you have on today's event, either directly in the chat on Discord or reach out to any of us personally. And that's a wrap for Coconut, for Recurrent Depth, for LRMs. I'll look for more LRM series stuff coming. We've got some other series we're cooking up. So keep building, shipping, and sharing in the meantime. And you know that we will do the same. Have a great week, everybody. See you next Wednesday.